We've been discussing the polar coordinate system in our last couple of videos, and in our most recent video, we talked about how to find derivatives in the setting of polar equations. Today, we'd like to continue that theme and discuss how to calculate area and arc length in the setting of polar coordinates. Let's go to the whiteboard. So we've spent some time discussing the polar equation r equals 1 minus sine theta. And here's the graph that we wound up building after a little bit of careful analysis. And so today, let's see, we want to begin by talking about what the area of the region is that is bounded by the graph of this polar equation. Now, we could do some estimates, and I kind of like to do that sometimes before we get started so that we can get a sense as to whether our answer agrees with intuition whenever we finally build it. So let me give a rough estimate of, let's say, this side of our graph, the region that is given to us by this triangle. And I use a triangle because its area is very simple to calculate, 1/2 base times length, or 1/2 base times height, however you're thinking of the units, the measurements here. So let's see, we have, that would be 1/2 times 1 times 2. So 1. So the area of this triangle is about 1 square unit. And let's give a little bit of a better estimate. Let's pull this triangle out. And this looks like, so this triangle has a height of a little more than 1, and it has a width of 1, right, from here to there. And so a little more than 1 times 1 times 1/2. So this is going to be a little more than 1/2. By the time we put these two pieces on, we're probably going to be up to maybe about 3/4, let's say. 3/4, what does this estimate to be? This probably is about maybe another quarter of a unit. So let's see, what do we have? A quarter, maybe about 3/4. So that's what? That's 1 in addition to our 1 here. And I think I underestimated that just a little bit. Let's go a little more than 2. So a little more than 2 for the area of this region right here. And then over here, that's going to be another little more than 2. So roughly something a little more than 4 is probably what we would expect to get whenever we calculate the area of this region. All right, so how are we going to go ahead and give a precise calculation? Well, we're going to use the calculus principle just like we've been using all semester. We're going to begin by dissecting the region into different pieces. So again, we're using the calculus principle. And you'll recall that's dissect, analyze, and reconstruct. So we're going to dissect it first. And we could, I suppose, dissect into rectangles. That's probably going to be your go-to shape. It's usually my go-to shape. But in the setting of polar coordinates, that would be forcing a shape that is simple to calculate in the rectangular coordinate system into a setting where we're using a different coordinate system, polar coordinates. And polar coordinates don't deal with rectangles particularly well. So I think it's going to be better to dissect into some shapes that are more amenable to the coordinate system that we're working in, to the polar coordinate system. And so here's what I'm going to do. I'm going to, for some angle here, And this angle would be, I guess, from here all around to there, so whatever that angle is. And I'm going to, well, just like in the rectangular setting, whenever we did do rectangles, we looked at a y value and kind of pretended it was the same over some interval and built that rectangle. Well, for this r value, we're going to pretend it's the same over some little interval. And look at the shape that results. So if that r value is the same over that little interval, what we have here is a little sector of a circle. And I have a little change in my angle there. So I'm going to label that as a little delta theta sub I. I'm going to label this radius as an r sub I. And that looks a whole lot more amenable to the polar coordinate system. It wouldn't be a very nice shape to dissect into if we were using rectangular coordinates, but it seems exactly the shape we should be dissecting into whenever we're using polar coordinates. All right, so we'll assume that we have dissected the entire region into, what would these be? Circular sectors? Right? So after we've dissected, we need to analyze. So let's go ahead and analyze how to calculate the area of a circular sector. And we've done something similar to this whenever we reviewed how to find arc length of a circle. And the idea was this. So if I have an area that's given to me by a particular angle, and let's say I doubled that angle. Well, if I double the angle, what happens to the area? Of course, the area doubles also. And so if I have the angle, the area halves as well. So one way of saying that is if I take the area and divide it by the area of another sector given by another angle, if this is, right, so if this was, here my A is my original sector, if my A prime were the area of this larger sector, then let's see, A over A prime would have been 1/2. But theta over theta prime, right, so theta prime is this entire angle here. Theta over theta prime is also going to be 1/2, right? So these ratios are going to turn out to be the same. And then we look for a particular sector that we know a lot about. And the sector that we know a lot about is the sector given to us by the full circle. And so if I use that one, then the area, let's see, so I'm looking for A, but the area of that larger sector, the area of the whole circle, is pi times the radius squared. And the angle of the entire circle is 2 pi radians. And so that gives me enough information to find A in terms of theta. I'll just do a little algebra here. So this implies that A is going to be, well, let us see, this is pi r squared theta divided by 2 pi. Well, but that just gives me, so the pi's factor out as a 1, and I'm left with 1/2 r squared theta. Great. Okay, so that's how to find the area of a sector of a circle, and that's exactly what we have here is a sector of a circle. And so its area, the area I'm looking for up here, so the area of a typical sector is going to be, well, it's going to be 1/2 times the radius, which in this case is r sub I, squared, times the angle. And the angle is this delta theta sub I. And so there we have it. We've dissected into circular sectors. We've analyzed the area of a typical sector. And so finally, what we need to do is put all those pieces together and reconstruct. So we've dissected, we've analyzed. Now let's reconstruct. And whenever we reconstruct, that's going to be what? The sum as I ranges from 1 to however many sectors I'm working with here of 1/2 r sub I squared delta theta sub I. And so in our particular case, r sub I is going to be 1 minus sine of theta sub I. And I have that on the next page. We'll just go right to there since I'm running out of room on this page. So let's see, what are we looking for? The sum of 1/2 times 1 minus sine theta sub I times delta theta sub I. And that's exactly what I've got right there. So whenever we reconstruct, we have the approximate area of the region being this sum. Okay, now we finished with the calculus principle. Now we're going to use Newton's genius that told us that if we're able to express a quantity approximately as a Riemann sum, then we can evaluate it precisely as a definite integral of that function. So let's go ahead and evaluate this integral. This isn't too bad. We've seen integrals like this before. So I'm just going to expand the 1 minus sine theta squared. And let's see, these two pieces are easy to integrate. This one I'll probably want to use a trig identity. So 1 minus cosine 2 theta over 2 is sine squared theta. And so at this point I can find an antiderivative, and I'll evaluate it at 2 pi and at 0 and subtract. And whenever I do that, I get 3 pi over 2 square units. Well, let's see, does that agree with our estimate? Our estimate, I believe, was a little more than 4. And 3 pi, let's see, 3 pi is just a hair more than 9. 9 over 2 is 4.5. So looks like our estimate agrees pretty well with the actual value of the actual value of the area of this region. So let's recap just a little bit. What did we see? Well, we saw that if we're going to calculate the area of a region given to us by a polar equation, we can begin by dissecting into circular sectors, and then by the fact that the area of a circular sector is given to us by 1/2 times the radius squared times the angle, we can build a Riemann sum, which gives us the approximate value of the area. And since this Riemann sum gives us approximately the value of the area, we can evaluate the area precisely with the definite integral. Okay, let's move on to arc length. So let's begin similarly by looking at a real rough approximation as to what it is we think we probably ought to get. So let's see, if the distance from there to there is 1, what would the length of this arc be? Certainly a little more than 1. Let's see, if I stretched it out a little bit, looks like it would lie maybe up to maybe about there. So that's what, maybe 1 1/3, 1 1/4, something like that. So let's see, let's just go with 1 1/4. So there's 1 1/4, another 1 1/4. So that's about 2.5. Let's find another length 1 along the arc. So 2.5. There's another length 1, so maybe 3.5, 4.5, 5.5, 6.5, 7.5, maybe a little more than 7.5, roughly 8, somewhere in there. Okay, so whenever we get our final answer, if it's somewhere around 7, 8, 9, we'll be pretty confident that what we did was correct. So let's go ahead and evaluate this. All right, so again, we're working with the polar equation r equals 1 minus sine theta. And you'll recall that we saw in our last video that we can express this curve parametrically, right? That's the way we found derivatives, dy dx, whenever we were in the polar setting. We expressed it parametrically by using that polar to rectangular conversion equation, right? That x is r cosine theta and y is r sine theta, right? You remember those conversion equations, but we're able to apply it in the polar setting here because r is 1 minus sine theta. So I can find a set of parametric equations which gives me the same, whose graph is the same graph of this polar equation by just replacing what r is into our polar to rectangular conversion equations. And so what I'll have is, instead of x equals r cosine theta, I'm going to write x equals, well, 1 minus theta cosine theta. That is r in this case. Y is r sine theta, but r is 1 minus sine theta, so y is 1 minus sine theta times sine theta. And I would encourage you at this point, actually, this is just to kind of emphasize what it is we're doing. Dig out a calculator, turn it on, and let's go ahead and graph this curve both in the polar setting and then in the parametric setting, just to see that what we're doing, what we've just said, really applies. It really works. So I'm going to go to my mode. Let's see, right now, probably your mode is set to function. Whatever it's set at, go ahead and set it to polar coordinates, and then go to y equals. Sorry, let's go back to mode. I didn't hit enter. So polar coordinate, enter, and that puts us in polar mode. So now whenever I do y equals, it prompts me for r. Well, my r is 1 minus sine theta. So let's go ahead and just type that in, ask it to graph it. Make sure that your window is set to something reasonable, and mine is set for thetas between 0 and 2 pi. And it looks like my x values are, I need at least from about -2 to 2, and I have -3 to 3. That's going to be fine. My y values I'm going to need as low as -2 and as high as, well, certainly 2 is plenty high. So that should be good. Make sure your window is set and then ask it to graph. And there it is. There's the graph of 1 minus sine theta, the heart that we get. And then go ahead and shift the mode to parametric equations. And go to y equals. I already have these typed in to save a little bit of time. So 1 minus sine theta times cosine theta is my x. 1 minus sine theta times sine theta is my y. You see t's here instead of theta. That's completely unimportant. It doesn't matter what we call our parameter. And the calculator is defaulting to the variable t. And whenever I graph it, sure enough, it sketches the graph that we're working with. It sketches our heart. So I encourage you to play with that a little bit, just for fun. All right. So we also saw in the video on parametric equations, whenever we were looking at calculus in the setting of parametric equations, that we can find the arc length from, we're working with theta being 0 to theta being 2 pi, by using this integral. And I would encourage you to go back and review that video to see where this all came from, but I'm not going to review it right now. So what we would need to do is, so we'd be looking at dx d theta. So here's x. So dx d theta is going to be the derivative of this function. dy d theta is going to be the derivative of this function. And it's going to be a bit of a mess, I'll have to say. But I would encourage you to go ahead and put that mess down. Go ahead and take these derivatives and square them and add them together and try to simplify and see if you can find the integral of the function that results. It will really test your mathematical skills, but I think it's a nice exercise. I'm not going to carry out that exercise because it turns out, and this amazes me, this happens so frequently in mathematics, that it's often far more difficult to do a particular problem than it is to do the problem in complete generality. Instead of r being 1 minus sine theta, I'm just going to let r be a general function of theta, f of theta, right? So 1 minus sine theta is going to be one of these, but I'm not going to specify it. And so the work that we're about to carry out is going to apply to all functions, and it's going to turn out to be much simpler to do. So here we go. So I need to find, let's see, what was it? It was that I needed to eventually need to evaluate the integral that involved the integral of the function square root of dx d theta squared plus dy d theta squared. All right, so I'm going to need dx d theta. Well, whenever I find dx d theta, that's just a simple product rule. So I took second times the derivative of the first, plus first times, and then the derivative of the second is negative sine theta. So whenever I add it, I'm going to get negative sine theta f of theta. And then the derivative of y with respect to theta is same thing, right? Second times derivative of the first plus the first times the derivative of the second. And so I need to square those. I need to add them together. So let's go ahead and do that. Whenever I square dx d theta, I'm going to get, let's see, so this is going to be the first term squared times f prime theta squared minus twice cosine theta f prime theta sine theta f of theta. Running out of room. Plus sine squared theta f of theta quantity squared. And whenever I square dy d theta, I'm going to get sine squared theta times f prime theta quantity squared plus 2 sine theta f prime theta cosine theta f of theta plus cosine squared theta times f of theta quantity squared. And so whenever I add them together, let's see, dx d theta squared plus dy d theta squared. That's going to turn out to be, so I'm going to add these two together. And so let's see, adding these two together, I could factor out f prime theta squared. And I'll be then multiplying that by cosine squared theta plus sine squared theta. Oh my gosh, that's 1. So whenever I factor out f prime theta squared, I'm going to be multiplying that by 1. Awesome. So that simplifies markedly. These two terms, except for the signs, are identical, right? 2 cosine theta, f prime theta, sine theta, f of theta. 2 cosine theta, f prime theta, sine theta, f of theta. Whenever I add these two together, I'm going to get 0. Whenever I add these two together, I can factor out f of theta quantity squared. And I'm going to multiply that by sine squared theta cosine squared theta. I multiply by 1. Oh my gosh. The sum of these two derivatives squared, the sum of the squares of these two derivatives is just this. Now, if you took my advice earlier and tried to simplify the mess that we would have gotten by doing this for these particular x and y values, you will really appreciate what's just happened here. So what do we have? So we know that the arc length that we're looking for, actually, let's stay in the full general case here. The arc length of the graph, the polar graph of r equals f of theta is, well, let's see, it's going to be the integral from, well, in the case we're doing, it's going to be 0 to 2 pi, but in general, we'll start at some angle and end at some angle, of the square root of, and instead of writing this down, I'm going to write this down, f prime theta quantity squared plus f of theta quantity squared. And so that is enough to get you to evaluate the arc length of the graph of any polar equation. Let's do the one we're working with in particular. So for our case, right, we're working with r equals 1 minus sine theta. Right, so, and our theta is ranging from 0 to 2 pi. And so the result that we just developed for our particular case is going to be, so let's see, so here's f of theta. So our f prime of theta is negative cosine of theta. And we're going to square that. So whenever I square negative cosine theta, I'm going to get cosine squared theta. And then I'm going to square my function, 1 minus sine theta quantity squared. That's the integral. We just need to evaluate it. Okay, so let's go ahead and carry these steps out. Here we go. The numerator is going to be cosine theta exactly on the intervals on which cosine is positive, and that is the interval from negative pi over 2 to pi over 2. So that would give me the left hand, or the right hand portion of my graph. And by the symmetry of the graph, I'll then double it. And that'll give me the entire arc length that I'm looking for. Which is 2 times 2 times 2, which is 8, which is right at where we estimated the arc length was going to be whenever we started this whole procedure. So there we have it. The arc length of our heart is 8. The area of our heart is just a little more than 4.5. And that is our discussion on area and arc length in polar coordinates. I hope you enjoyed that. I certainly did. And in general, I hope that you have enjoyed this whole calculus series. This will be our last video in the series. So we will not meet again in this manner. So please stay well, stay safe. Good luck.